basically, I want to talk to you today about the application of benchmark protocols, different benchmark protocols to the design of the clash hand that we have developed at the Institute of Robotics and Mechatronics and DLR. So let me start by mentioning something about the ways that we have for measuring the performance of robotic manipulation systems. So basically, establishing some experimentation methodologies to compare results across different groups is still a challenge that we have in robotics. And for testing the advances, we usually rely on competitions and benchmarks. And this table compares basically some aspects of both of them. So competitions, for instance, provide a fixed set of rules and in most cases some predefined tasks and expect solutions that solve the challenge in an efficient way. So the risk that we have with competitions basically is that some teams can over-engineer the solutions to solve the desired task. And this, of course, limits the applicability of the methods outside the scope of the competition. On benchmarks, on the other hand, we usually have established procedures for testing different aspects of robotic manipulation. And the idea is to guarantee repeatability and reproducibility of the results. These benchmarks in general can be executed anytime, and the results are evaluated either by the team or by some judge, but following an established protocol. Here, this is a table that we published on a paper on RAL last year, which summarizes some of the existing competitions that involve robotic manipulation in some way. Most of them, actually, if you see, they use a fixed set of tasks for the competition design. And well, this has the advantage that it allows to create interesting scenarios that enable the progress to be measured objectively based on the task performance. So competitions are crucial to the community, in my opinion, and some of them actually we know have been very influential for developing certain applications, for instance, in logistics scenarios. Benchmarks now, in terms of robotic manipulations, can be classified in these three different levels. So I introduce here the mechanism level, where we have measures that benchmarks that measure the intrinsic capability of the mechanisms, mainly the hand or the gripper. We can measure, for instance, robustness and resilience of the hands or mechanical properties, such as fingertip force or gripping force. At the algorithmic level, we can evaluate a specific part of the manipulation pipeline. For instance, the grasp planning stage, the motion planning for the full arm, or the object recognition and pose estimation. But in most cases, we are interested in things at the system level. So that means considering the performance of the robotic system as a whole, solving autonomously certain tasks, such as the box and block test, or picking up place in certain objects in logistic scenarios, or picking from shelves. And a nice summary of a lot of benchmarks that were proposed for manipulation is summarized on the special issue in 2021 on robotic manipulation. So this is a collection of 14 different benchmarks, for instance, for bimanual manipulation, in-hand manipulation, or grasp planning algorithms. And of course, I encourage you to take a look to these papers and see how can you use these benchmarks to measure the progress in your research. But today, I wanted to present to you how we use benchmarks for the evolution of the design of the clash hand. So let me start by showing this video. This is an example of the ideas that we had in this project, SOMA. SOMA stands for soft manipulation. So we work with different partners, mainly with Ocado Technologies in the UK. And the idea was to develop an N effector that could exploit what we call environmental constraints. That means explicitly exploiting contacts with the environment to guide the manipulation actions or to grasp difficult objects. In this slide, for instance, we see two of these constraints. The one that you are looking at right now is what we call the wall grasp, meaning that we basically push the object against the side of the container to be able to grasp the punnet in this case. And here on the right side, we have what we call the edge grasp. So for grasping such a thin object like this ticket or a business card, the hand basically slides the object towards one of the edges and then grasps the ticket. Good. So this was a couple of examples of the application of the clash hand. Let me show you quickly how the hand is constructed. So clash stands for compliant, low-cost, antagonistic servo hand. The design follows the idea of embedding variable stiffness actuation into a robotic end effector. So to enable this, we created these two modules that you see here on the left and the right column. This is a module for two fingers, so for parallel fingers, and then there is another module that we call the thumb. Each module has 4 motors. 3 of them are used for, well, changing the flexion and extension or the abduction degrees of freedom. And one of them is used for changing the pretension of the tendons, which basically changes the joint stiffness and allows the fingers to be very soft or very stiff, depending on the application. Now, here you see how this variable stiffness is implemented with what we call the flexible antagonistic spring or FAS system. And this enables a very high sensibility of the hand, as you see in this video. So this is a normal business card. And you see that as soon as we touch the card, the fingers try to wrap around the object to increase basically the number of contact points with the object. And then we tested the robustness in a bit of a savage way. So having a hammer and then hammering the fingers and see if the hand was actually functional afterwards. And well, luckily we did an evolution of this test that you will see in a moment. In this slide, I just want to show you some snapshots of the performance of the hand. So here we can grasp a very large variety of objects. So you see here some objects of the YCB database, and in the video on the top right, different objects using some combination of these primitive motions that I described before. So a net of limes or this plastic bag with salad. And here on the bottom, you see, for instance, grasping one whipped cookie. So we can also apply grasps with very low forces to avoid destroying such delicate objects. Good. Now, you saw before one rough version of the robustness test, but of course, oh, sorry, I went too hard. We tried to make this more systematic, and here you see the result of these tests, this benchmark. So basically, we worked together with IIT in Italy, and we developed this benchmark for measuring the performance of the hand in a more suitable way using a pendulum mechanism similar to the one that is used in for testing the resilience in mechanical proofs. So we were basically considering two different aspects: how the hand behaves under dynamic loads and the grasp resilience, or how the dynamic loads affect the hand's grasping abilities. So basically, that's this test on the top. We have a grasp object, and then we hit the object with the pendulum, and we verify if the hand can still grasp the object after the initial hit. Oh, sorry, the video is not playing for some reason. Well, but you can imagine there is the same idea of the pendulum hitting the object, and then the hand can still grasp the object. So we measure things like what we call transmissibility. So basically how much of the impact is absorbed or transferred by the hand at the base, and then the absorbed energy. Good. We also had some different way to measure the grasp performance, and this was this test from this reference, where we basically try to quantify how good the hand is to grasp an object using different approach directions. And this is visualized in these heat maps. So basically in the horizontal axis, we represent the approach direction, and in the vertical axis, we represent the orientation of the hand that you see sketched here on the left side. So basically on these heat maps, white represents very good performance of the hand and black represents poor performance. So the idea here with these multiple maps was that we were interested in studying what happens or how the hand performs when a failure occurs. So we introduce multiple failures in the hand, for instance, a motor or a sensor failure or breaking a tendon, and then we were adopting some suitable hand compensation action once this failure was detected, and we tried to run the test and see how the performance of the hand was affected by this failure. This slide shows you the implementation of these error recovery strategies. So basically, we have some initial tests at the beginning of the operation, for instance, in the fast pull-up test or the servo pull-up tests, where we can detect very quickly if there are disconnected force sensors or the tendon is broken. During the operation, we can also do some tests. So verify as well if a tendon is broken by increasing the passive stiffness of the system, and then we compare this stiffness with the nominal and the real spring deflection. The servos can also be compared, well, measuring basically if the commanded and the real positions match within an allowed threshold. And we also check the grasp success. So basically, we adopt these hand-coded strategies to recover typical failures, the failures that we introduced, and we saw how the hand was performing. So in the figure on the right, you see the comparison of the performance. In blue is the nominal performance using only a force torque sensor or using a proximity and a force torque sensor for performing different grasping actions. And then in green, these bars show how is the performance after one of these failures. So for instance, there was one tendon that really greatly affected the performance of the hand. Good. Now at the system level, we also wanted to measure the performance of the system, of the fully integrated robotic solution. That means the arm plus the hand, plus the vision, plus the grasping planning, plus the control, while grasping and placing different fruits and vegetables. So to obtain or to make a systematic benchmark, what we did was proposing different scenarios of increased complexity depending on the level of what we call structure clutter on this logistic scenario. So you see here we have low clutter scenarios where the objects have enough distance between them and with the crate, but we can go to high clutter scenarios where the objects are very close together. And the idea is to reach this level on the last row, the real scenarios where there are multiple layers of the same type of objects coming into the warehouse. Good. So following this benchmark, we basically compared the performance of 4 different hands and grippers that we developed within this project in SOMA. And you see here actually the hands. There is the PISA IIT soft hand, then the PISA soft gripper, the Clash hand, and the robotic gripper from Technical University of Berlin. And basically here we compare different aspects, for instance, the success rate for the different scenarios that we saw before in the previous slide, and the type of failures, which is actually quite interesting. So the Clash hand is the orange bar, and actually we saw that it didn't perform as well as we expected compared to the other hands. So this was in principle a bit disappointing, of course, but we actually took this as a chance to improve the design of the hand. That's the beauty of these benchmark protocols. On the bottom figure, actually, you can see the types of failures. We classified the manipulation action in different stages, and we saw that most of the failures were happening on this grasp stage, meaning there was some problem when you were actually trying to grasp the object. But there were also some other failures, for instance, in the transportation stage, or even system failures, what they call system failures. So some failure in software or some error that was unexpected. Good. There were also some interesting things with this benchmark. So for instance, none of the systems that we tested was capable of solving this high clutter scenario. And well, there are different reasons for this, but basically solving these very cluttered scenes for the logistic domain requires a combination of different factors. Of one of them is vision, for instance, and we saw that, for instance, learning-based solutions are very good for detecting instances of objects in the medium and low clutter scenarios, but several state-of-the-art algorithms cannot detect all the objects in the crate. So they can detect some of them, but obviously if you didn't detect all the objects, you cannot grasp all of them. So this was an interesting finding from this benchmark. Good. So the idea here is, of course, we need to have better vision system, and actually, well, we have been exploring different state-of-the-art solutions, even commercial solutions. And well, there are actually some solutions that now we have discovered in the last months that can deal with these type of scenarios. However, there are very challenging things like these salad bags, where differentiating where one of the bags is finishing and the other one's starting is kind of tricky. But okay, for these high clutter scenarios, you can come up with handcrafted strategies like the one that you are looking at in this video, where you introduce the finger in one of the holes between the punnets, and then you slide the finger along the edge of the punnet. You try to lift it, and then the punnet is turned 90 degrees, and then you can grasp the punnet and put it away. So of course you can do these kind of things, but the goal is to make this in a systematic way with an automated pipeline. So we created this. We were working on what we called environment-aware manipulation planning, which is basically a combination of different things. So we combine a grasp sequence planner that identifies what are the objects that are easier to grasp in a given scenario, a finger stiffness planner that exploits this capability of having variable stiffness on the hand, and a finger position planner that adjusts the finger position for these very cluttered scenes where there are very limited free spaces around the object. We implemented this, and here you can see, perhaps let me just skip to the final slide. You can see how the system performs in different scenarios with different objects. And well, the system actually performed quite well, but we also want to move towards having a more generic solution. So we still feel that the implementation that we have is very suited for these type of scenarios that we had in the benchmark, and we want to move now to more generic scenes. However, let me conclude with one more iteration on these benchmarks. So for these highly cluttered scenes, we saw that having tactile information at the fingertips is really essential. So we started to play with different tactile sensors, resistive sensors, time of flight sensors that could be fitted to the fingertip, and try to use them for solving these scenarios. And we implemented actually this for this scenario, for instance, the cucumber. We adopted a different vision pipeline here, just a watershed vision algorithm for detecting individually each one of the cucumbers. And with the information coming from the fingertips, we could actually detect things like when the cucumber is rotating inside the gripper, so that you can consider this in the transportation phase to avoid dropping the object in the meantime. And with this video, I want to show you one of the topics that we are actively working on is how to enable the system to automatically recognize these errors that happen when you are executing one action. So I'll play this again. For instance, here, this is a simple example. We try to grasp the object slides because the stiffness that we set was too low, and then it tries again, adjusts the stiffness, and then it succeeds. And with this kind of approach, we actually could solve this challenge of emptying the bin, basically. So if this is a topic of interest for you, I would love to exchange ideas about this. This is really a key topic for us right now. Good. So let me conclude the talk with some takeaway messages. One, well, variable compliance allows a very nice adaptation of the hand to different objects. And in the clash hand in particular, we can independently tune the forces and stiffness without changing the fingertip position, which is an advantage of the mechanism that we implemented on the clash hand. Then we use a variety of benchmarking protocols that actually help us to improve the design, and we are still actively using them in two new European projects that we just started, following up on this idea of improving the performance in logistic scenarios, both in the fruits and vegetables case and also with deformable objects nowadays. Then we have, of course, this combination of sensing and manipulation planning that help us to solve this challenging scenario, the benchmark. And there are still some different points that are open on our side to obtain a generic manipulation system, even for the solution of this system level benchmark that we were using as a guideline for this development that we had. Anyways, at the end, we definitely think that benchmarks are an effective tool to improve the performance of robotic systems. And as mentioned before, I encourage you to take a look to already published benchmarks and try to use them for advancing your work. With that, I conclude my presentation. So this is just a quick acknowledgement to the teams and the companies that participated in this project, and then my contact details. So thanks for your attention, and well, I'm happy to take some questions that you might have. Thank you very much.
I think we have time for one or two questions. Any questions from the audience for Maximo? Yeah.
How do you bake in things like damage?
How do you
think about damage?
The question is, how do you think about damage in these hardware systems during the benchmarks?
Damage in the system or in the objects that we are manipulating?
I guess when you're benchmarking your task, are you trying to optimize or like reduce damage that you're causing to the items?
As about to the items.
Oh, yeah. So this is a really nice question. Actually, that's why we developed this hand, because in logistics, well, you know, if a customer receives an object that is damaged in some way, the object is basically returned to the warehouse. And this is a huge loss of profit for the company. So the variable stiffness allows the hand to apply just the minimum force that we need for grasping the object. We basically have some object database below the manipulation planning layer that indicates if the stiffness and the force that you need to apply are low, medium, high. So we have some different thresholds. And that's the way that we are dealing with this topic right now. We actually, in one of the projects that we started, we are exploring the idea of measuring this damage that you can create on the fruit or vegetable and try to correlate this with the force that you are applying to the object. This is a very challenging topic, mainly if you consider, for instance, fruits. Sometimes it happens that during the manipulation action, you don't see the damage. So you just grasp the object, you place it, and you don't see any evident sign of damaging the object. But turns out that it appears just after a few hours, and then the customer receives the object and is already having some marks. So this is really bad. So it's an interesting topic, and we are working on it. So hopefully on the next occasion, I can present you some initial results of this approach.